Alright, welcome to the video everyone. So I basically made this video if you're struggling with Calc 2, ODE sections of differential equations, or if you're starting your Elementary Differential Equations course and you're feeling kind of lost. Hopefully this is the right video for you. So let's get into it. So again, I made this presentation just to make the underlying mechanics of ODEs a little more clear and hopefully give you somewhere to start and some guidelines to go about solving these problems and making sense of them and what you're supposed to do and so on and so forth. So yeah, I really hope this video helps anyone that is lost. The assumptions here, I'm just assuming that you have a basic working knowledge of calculus. You don't have to be an expert. We're not going to do anything too crazy. Just some basic integrals and derivatives, and then how to do basic algebraic manipulations. So hopefully any of the calc or algebra or trig in this video is simple and you remember it all. All right, so our little agenda. First, we're going to discuss the general goal of ODEs. So if I hand you an ODEs problem, what are you doing? What are you solving? What are you looking for? I sat down with several students that couldn't answer this question of, hey, I give you this problem, what are you solving for? They had no idea. So hopefully if you're kind of in that same boat, you don't really know what's going on, we'll look at that. We'll clarify some of the commonly used notation throughout ODEs courses. Not understanding this notation, can be really hindering to your understanding of the topic as a whole. So hopefully by clarifying how to use all these different notations, all of this will become a lot clearer. And then we'll also work through some nice basic examples to hopefully tie this all together after we've gone through some theory. So what are we studying in ODEs? So let's be super clear. In calculus, I give you a function. I give you some f, and I say, hey, find f prime or f double prime, right, taking derivatives of f. So in this example here, this first one, we just have f of x equals x squared plus x, right? Take a derivative, we get 2x plus 1, right? So calculus, I'm saying, here's a thing, take a derivative, right? That's one of the big steps in calculus that we learn how to do. Or if you kind of go on in Calc 2, right, you start looking at antiderivatives or integrals, and we get a function f, right, taking the integral or double integral of it. So an example would be, right, if the function is cosine of t, then the integral would be sine t plus c, right? So this is calculus. I give you a function, and then you give to me whatever the derivative or integral of that function is, by and large, and then you do things with it. ODEs, we're kind of going the other direction. We're saying, if I give you an equation, which has, say, x, f of x, f prime of x, so on and so forth, give me some family of functions, f, that makes the equation true. So here, we're not solving for, all right, I have f, take a derivative. We're saying I have an equation with some derivatives in it, right? So if we look here, right, there's an f prime in this equation. Now solve f for me, so give me f. So that's kind of the big thing we're doing in ODEs. So if somebody gives you some generic ODE, the solution you're typically looking for is, hey, find some function that satisfies that. So, right, if we take the derivative of this again, which is very similar to this guy up here, it would just be 2x plus 1 plus 0, right? Derivative of a constant 0. So this would satisfy this equation here. All right, so let's start off with a really simple real world example here that we could think about, and we'll just have it be dumping water into a pool. So say we have some nice big hose here, and it's just dumping water into this pool. So say like every second that goes by, 1 more liter of water goes into the pool. So this would be a really nice, simple linear relationship. So we have liters in the pool, and we have time in seconds. So every second that goes by, we get a liter. 1 more second goes by, we get another liter, so on and so forth. So we just see this really nice, y equals x type line, or y equals t. Right, and the slope or rate of change is just 1. So if we have this equation here, so we have y equals 1, right, this is our slope, times t plus 0, right, we're starting at 0. That's just going to be a nice simple equation, y of t. If we take the derivative, like we would be asked to in calculus, you get y prime equals 1, right? So at any point, at any instantaneous moment of time, the rate of change is this constant equal to 1. But what if we only have the ODE, right? So In this setup, right, I'm telling you, okay, we start at 0, we start putting water in there, great. But what if I only have this piece here? So in order to figure out that equation, can we go backwards? And in this simple example, we can, right? So if we take an integral of y, take an integral of 1, we'll get to this equation here, y equals t plus c, and we'll have solved this equation, right? But this c is kind of doing a little bit here. It's making this slightly more complicated. In this example above, this c is 0, right? Because we're starting at 0. But here it's left nondescript, right? Because if I take the derivative of y prime is going to equal 1 plus 0, right? So this c could be anything. It could be negative a billion, it could be 0, it could be pi, it could be 100, right? So this c is kind of doing a little bit of work in the background and is related to whatever the initial setup of our problem is. And we'll talk about that more later on. But yeah, so in this simple setup, we know that c is however many liters of water we start in the pool with at time 0. Right, so this c here is 0 if we start with nothing, but if we said, hey, make this 1, go up to 1, and we'd have a nice straight line coming up through here, right, and that would be y equals t plus 1, right, same derivative though. And we can kind of think of this as a useful example, right, because look at the shape of this pool, right, it's kind of got these wavy edges, there's clearly a drop in this section here. So if I just filled up this pool with water and said, hey, how many liters of water are in here? This becomes like a really not trivial problem, right? If you go to any pool that's not a nice cube shape, right, however much water is in that pool, that's going to be not trivial to figure out. So if we can find instead a flow rate, right, and know that we're starting with nothing, we might have a much simpler expression to deal with. So this example, which is nice because it's easy to work with, is also kind of practical and can be helpful for understanding basic problems and basic problem setups. So that's kind of what we covered here. So let's try this with something more difficult, right? Because we're kind of talking about how calculus is going one way and ODEs are going the other, going sort of backwards. Can we do that again? So we have, say, y prime plus y double prime equals t. All right, we'll take an integral. So if we integrate this, we just get y. Integral of this again, we're just going to get y prime. The integral of t over here, right, it's going to give us this slightly more complicated equation, right? So that's just taking the integral of t, we're going to get 1/2 t squared plus this constant integration. All right, take another integral, we're going to get y as an integral, right? Because this is nothing to script yet. We'll get just plus y here and plus this whole expression over here. But this isn't helpful, right? So we have an integral of y dt, but we don't know what y is. We don't know anything about y. We don't know what the expression for y is. So if you get to this point anytime you're solving an ODE, that kind of means you need to try again, right? This is highlighting to you that you've made some critical mistake. And so this just sort of take an integral or take a derivative, go forward or backwards technique really doesn't always work for us. So we kind of need better tools. And that's what ODEs is. It's just a bunch of different techniques and tools to try to figure out, hey, what is some nice clean expression or analytical expression for y? All right, so let's look at the most basic part of the problem. So the object y, right? It's really important to note that we shorthand a lot of things in math, and in ODEs, when you shorthand stuff, if you don't know what the shorthanding is from, you're going to be in a lot of trouble. Things are going to be really confusing. So here, if we instead have y, we're going to note that this equals y of t, right? So you've probably seen this notation before. This y of t just means that y is a function of t. So I plug in some t, it gives me a y, right? That's what this means. So a basic example, if we had, say, y equals t squared, right? We've all seen something like this before, right? Y equals x squared. We've graphed this a million times, saw this in algebra. Cool. Should we go with this, right? So we'll expand this notation just a little bit to make it more explicit, right? So y of t equals t squared. And then something we want to do, so say we want to figure out what's the value of this if t is equal to 2. What we're really doing when we write this notation, so you've probably seen notation like this before, but this is acceptable, right? So putting y equals t, or y of t equals 2, this here is notation that I've used before in papers that really helps clarify what it is that you're doing and what's being set to what. Excuse me. And so when we have y of 2, that's saying y at t equals 2. We plug in 2, right? 2 squared is 4. So that piece should be easy, right? And if I just kind of told you what is y if t is 2, right? You just kind of go, oh, I plug in 2, 2 squared is 4, right? So you kind of know that easily. But we're going to see much more complicated expressions, and understanding this bit here, that that's really what we're doing, is going to be really helpful. So this input t giving an output of y, right, leads us to the idea of dependent and independent variables in ODEs. And so I think before it was kind of simple enough to forget about this or not care about it, which makes sense, right? They'd talk about this and then just move on to a bunch of problems and it would sort of get washed out. But here in ODEs, it's really, really important to understand what is the dependent variable, right? In this case would be y, and what is the independent variable? In this case is t, right? So y is dependent, t is independent. And if we're thinking of real world examples, oftentimes in ODEs you'll see t used instead of x. And that's because t is usually standing for time. So here, this should make sense, right? The number of liters in the pool depends on time, right? We have a hose, we're putting the hose into the pool, we're filling it with water, right? So however much water is in the pool is dependent on how much time has gone by. But say like I have a neighbor who's got a pool next to me and he gets some pump and he's pumping water out of his pool, right? He didn't just invent a time machine, right? The world's cheapest and crudest time machine of just pumping water out of a pool and therefore time starts flowing backwards, right? That's not really how it works. This time is independent of whatever is going on with our other quantities. So time just sort of flows on, it does its thing regardless. And so time won't be affected by whatever's happening with y, whereas y will very much be affected by what's happening with time. So hopefully that's a little clearer as well. Also, if you're wondering, hey, can I have multiple independent or dependent variables? Yes, you can. That's why this little s here is here. So we can have systems of ODEs, which you might come to much later. Don't have to worry about it now. But you'd have, say, y of t and x of t and z of t. But if we have multiple things like t, so say like we have t, w and u or something, and these were all independent, then that gets into what's called PDEs, which are much more complicated and require knowing how to solve ODEs. So not part of the course, not part of this video that we want to talk about, but just know that you can have multiples of these and they just sort of change the different problem types you're working on. But for what we're concerned with, nice and simple, one dependent variable, one independent variable. This still leaves us a lot to learn and study, so we'll be sticking with one of each for now. All right, here's the thing that I found that confused students the most from my time as a TA when I was in grad school. So you have these two different types of notation. You have Leibniz and you have Newton. So before, in a lot of your courses, it probably didn't really matter which one was used. There wasn't much difference between the two. You just knew you were taking derivatives and integrals, and it just sort of was there, and you just kind of ignored it and learned, the route mechanics of how to do calculus. But here in ODEs, it's really going to start to matter. So this Leibniz notation is when we're writing dy and dt's out explicitly, or a d over dt with a y. And Newton is just compacting all that by saying, hey, we're taking a first derivative with y, or a first derivative with y of t, right, being even more explicit. But all of these things, every single one of them, they're exactly the same. They're telling you the exact same information, right? Here, I'm taking the derivative of y with respect to t. The operator of d over dt, right? Again, just a derivative with respect to t of this y here. This is just expanding out that y notation from like what we did earlier. So all of these things are telling you the exact same thing. So if you see this or you see this in here, you can replace it with any single one of these different notation types as it might be useful to you. And it will. We'll see it really shortly, that it can let us solve problems that we otherwise couldn't. Usually Newton is used in problems statements, right? Because it's nice and compact, right? This notation here is really small, really clean compared to say something like this. But when we actually want to work through the problem and solve it, this isn't going to be very helpful. This notation is going to be very helpful. We'll see that in a bit as well. So again, yeah, they're all just conveying the same thing. And lastly, for those of you who are more dynamical systems or physics focused, you'll see this y dot. That just means that we're concerned with time, right? So the dots are always just saying y, first derivative of y with respect to t with this first dot. If you see two dots, it's double derivative, so on and so forth. So again, this y dot would be the same as all this stuff here because our independent variable is t. All right. So let's make this last one super clear and note for second derivatives, you can do the exact same thing. So here you'll get this 2 up in the numerator, right? And you'll get the 2 on the t down here. And maybe if you've ever kind of wondered, why do I put the 2 on the d but not on the y, but I'm putting the 2 on the t? It's because this thing is operating twice on y. So we use this 2 notation, right, in this case, to show we're taking two derivatives with respect to t of y. So again, all of this is the same. All of these notation choices are exactly equal to each other. And same thing here. So if we have n number of derivatives, you've seen this notation before, right? With the parentheses, that's denoting derivatives. Again, all of these are exactly the same, and we're going to swap those out when convenient for us. So again, I saw this students really struggle with this idea, but just know all these different notation types are telling you the same thing. All right, so here's something that also is going to trip people up at first, but hopefully once you kind of get into the flow of doing ODEs problems, it's not so bad. In calculus, we really often forget this expression with the plus c at the end, right? So when we take an integral and we get this plus c on the other side, and this happens because it's not really used in calc. It's just sort of there. We don't really dive into it too much. And I even remember on exams, we asked our professor, hey, do we have to care if they didn't put the plus c at the end? Like, do we take off points? And he was like, yeah, it seems a little harsh. No, right? So like that's how forgotten about it was, right? But what we can do instead is now kind of reframe why this is important. And again, we saw that from that very first problem we worked on with the pool and the water, right? This plus c told us how much water was in the pool at the beginning. So if this plus c is forgotten, we're saying that there's no other solutions except for when c equals 0, which is not true. So we'll see where the c comes in, and where the c comes in is initial conditions. So if I say, hey, y of 0, right, again, we could put a t equals in here to really make this clear. Y at t equals 0, so 0 time equals 3, right? So that would mean that when we start off, the amount of liters in the pool at time equals 0 is equal to 3 liters, right? So that would be our initial condition here. So if our ODE problem gives us this, it's telling us, hey, this is the setup, then we know we're looking for one singular specific solution. If the ODE doesn't have that, if it doesn't give you something like this, it's just telling you, hey, find me a family of solutions or find a general solution for me, where if I then have an initial condition, sure, I can plug it in and figure it out, but you're just solving something in general for me at this point in time. So, and lastly, just kind of remember the difference, again, between definite and indefinite integrals. So if you have an a and b with some stuff in here, right, this is just a constant. So this is some number. If it's indefinite, right, no a and b listed, then whatever stuff we have, it's an expression, right, some equation, some function, some whatever, plus c, right? So this is important to keep in mind in ODEs as well. All right, so lastly, kind of went over this a little bit in the last slide, but to tie it together, what we have here is an initial problem statement where we have an ODE, right, where we have an ordinary differential equation, right, the differential because there's a differential in the equation of y prime equals 1. We saw this before. And the initial condition will be y at 0 equals 10, right? And we know this from, again, this would be 0, time equals 0, we have 10 liters in the pool, right? So this is the ODE, this is the initial condition. So if you've seen that written out before and you're kind of confused, that's just what we have here, right? We have an ODE and we have an initial condition. All right, so with all that theory kind of floating around, we'll just quickly recap it, right? Know the dependent and independent variables, understand the different notation for derivatives, right? Because we're going to use a bunch of the different notation. Don't forget the constant of integration, right? When you get those plus c's, those are very important. And then take note of your problem. Does it have initial conditions? Yes or no? If it has the initial conditions, solve for it, which is usually just one extra algebraic step. If it doesn't, leave it as is with the constant or the plus c or the c to the whatever still in there. Okay. So let's go back to this problem that we had before, right? We saw that it was nice that we could just sort of brute force an integral and it turned out to work. But then we also saw an example right after that where that didn't work. So let's see if we can solve this more explicitly in a way that kind of leads us to a better path of success for future problems. So we have this y prime equals 1. And again, so this y prime was equal to, right, the same thing as this dy over dt. So these two are the same. I haven't done anything except for rewriting y prime in this line. Then if we want to treat these like their own variables almost, right, or their own little objects or guys, we can just move this dt over. So this is called separation of variables. So you're going to see this a bunch in ODEs, and if you take PDEs, you'll see it in a different flavor, but same idea. So separation of variables is the most common technique for solving ODEs. So you basically are trying to get all of the stuff with y on one side and all the stuff with t on the other. So you're breaking apart your dependent and independent variables onto different sides of the equation. Then from there, we just take an integral. Right? I put these ones here just to remind us that there's a 1 multiplied by both of these guys. Kind of makes it easier for my brain. So we have this integral of dy, integral of dt. Right? So we're just integrating both sides. Basic calculus that you've done before. And you should get a y plus c1. Right? Don't forget the constant of integration. And t plus c2. Right? So integral with respect to t, integral with respect to y. So the y comes out, the t comes out. Right? And then these two guys are sort of floating, but the nice part is if I take just some random number and I add it or subtract it from another random arbitrary number, right, that's just some number. So if we see c2 minus c1, right, if I move this guy over to this side of the equation, I can just replace that with c because I just have constants being added or subtracted from each other. So this leads me to y equals, or y of t equals t plus c, right? And again, being clear here to denote in the end that y is a function of t. And this is the exact thing we saw before, right? We started, this becomes 0, so kind of, close one of your eyes on this guy here. We just get y of t equals t, and that's exactly what we saw before. And if we take a derivative of this, right, to just sort of check, does this make sense? We get y prime equals 1, right? Derivative of t with respect to t is just 1 plus 0, right? So this satisfies and it fits, right? And this here, this line, again, this would be our, our general solution, right? So it would be this number 2 line here, right? The general solution for this problem is just this, because we didn't specify what our starting condition would be. All right, so hopefully that's clear, and we have some of these core ideas down. Let's move on to a slightly harder example. So we have y prime equals y and y of 0 equals 2. So here's our ODE, right? And here's our initial condition. So let's first observe that the throw an integral at it technique, again, we're just going to see another example where this doesn't work, so definitely don't learn to rely on that. You integrate, right, you'll get an integral here. That's nice, that'll give you a y plus c, but if you integrate this side, you get integral of y, this is just a dead end. Anytime, again, you get to this, something looking like that, that should be a huge red flag to you that, hey, you've done something wrong. All right, so moving on, let's try to rework this guy here. So we'll try to use this technique that's taught in ODEs again in Calc 2 courses, separation of variables, right? You're going to see separation of variables ad nauseum over and over again. So here we go. So y prime equals y, right? The y can be left alone, so we'll leave it alone. This y prime becomes this dy over dt. Again, this Leibniz notation is much more useful. Moving this equation around, we want to keep the dy out of a denominator, so we'll leave this one on this side. We're going to move the dt over here. Move the dt over here and move this y over in this direction by dividing, right? So we get 1 over y, and we'll get dy equals, or 1 over y dy equals dt. So here, we just take an integral nicely, right? This is an identity, if you remember back to calculus, right? This 1 over y is just natural log, and this is really simple, right? This is just that 1 times dt. So we'll get t plus c2, we'll get natural log y plus c1, and again, these two are just constants of integration, so we're going to kind of lump these two constants together. And if we do that, I'll just call that a, right? So if that's same line as last time, move it over, call that a, right? So C2 minus C1 equals a. So now I have this expression here. A cheeky kind of move in ODEs is if you see an equation with natural log in it, try taking that entire equation to the exponent of e, because this expression here, anytime you have e natural log y, this, whatever's inside this natural log, just becomes that expression. So these two expressions here are equal with each other. And then you have e to the t plus a. So we have this expression here, e to the t. And if we're remember and careful with our exponent rules, we know this is e to the t times e to the a. But again, something nice here is that this e to the a, that's just some constant, right? E is a number, 2.7 blah, 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 something. And so e to some number, whatever that number is just, we'll just call that c. So we can rewrite this line here. I'm just putting it back there, and then boom, y of t equals c e to the t. So this is now what we've been looking for. Again, we're looking for some equation that just says, hey, this is y of t equals some stuff with some t's in it, right? A nice simple equation that we're used to looking at from things like algebra and calculus. And then let's kind of take a pause for a second. Does this make sense? Did we actually solve, right? This is the equation that we are looking to solve. So we go back up to this problem statement. We have y prime equals y. Did we actually solve this guy? And so I have y prime equals c e to the t. That was the solution we found. If we take a derivative, right? Derivative of e to the t is just e to the t. The constant stays the same. So this expression and this expression are equal. So we can see that y of t and y prime of t are the same. So you might have been able to guess this at first if you kind of looked at it and we're fast. But that's kind of how we go about solving it in a much more rigorous manner and working through the algebra and the calculus to get to this solution for this ODE. And again, a great way, this whole block here is basically just saying, if you get some solution, so say like you get this, but it's something much more complicated, go back to this initial equation, right, whatever your problem statement was, and just plug everything back in and take any derivatives that you need to do and see, does this come out equal? If it does, great, you found the solution. If it doesn't, then you need to rework something. But it makes it much easier to check, right? So taking derivatives and doing some algebra might be a little tedious, but it's usually a lot easier than actually solving some ODE, right? So doing two derivatives here and checking was much easier than this and all the work that we did, right? So we'll just finish that last piece. So the initial condition y of 0 equals 2. So we'll plug this in. So we get y of t equals c e to the t, right? So now we're saying, though, that y at 0 equals 2. So that means that this expression is saying t at 0 equals 2. So if I plug in y of 0 is equal to 2, right? I'm saying the left-hand side here is 2, but this t is equal to 0. So then if I simple out this algebra, right, e to the 0 is just 1. This 2 gets brought down there, so we get c is equal to 2, right? And so this is an important thing to note. If you get some initial condition or a set of initial conditions, and they say, hey, figure out what the equation looks like after we know that these are the initial conditions, you should no longer have any c's or d's or any sort of random constants floating around anymore. So we go from this expression to this expression. So here, this is something that is, again, this is our specific solution. This is our general solution. So we had to have some kind of initial condition specified, no initial condition specified. So hopefully that's nice and clear there. So in this example, right, if you kind of notice the pattern, whatever y0 equals here, so if we pick any number here, c just equals that number. So if we put 5 or negative 10 or whatever, that would then give that same number here. So we can kind of see when we're talking about families of solutions, that's what these look like. So if it was 5 or 3 or 2 or 1 or 0.5 or 0.1, right, we get all these different arcs and different lines. So that's what we're talking about when we say a family of solutions. So from earlier, from the pool filling example, right, it would just be a bunch of different straight lines up there. Sorry, 1 second. I left my dog out in the heat, and she was looking at me longingly from the door. So we have all these different possible solutions that are there. All right, and with that, thanks for watching. Hopefully this helps, and good luck tackling ODEs.